You know, they're everywhere. These microscopic architects of both chaos and, believe it or not, evolution. It's not really an organism, but it's not just a chemical either. It's something else. Today, we're going to take apart the virus, a nearly perfect biological machine that's built for one thing and one thing only, making more of itself. All right, so let's just jump right in with the biggest question there is. Is a virus actually alive? I mean, think about it. It can't reproduce by itself. It doesn't have a metabolism. You can literally crystallize it like a grain of salt. And yet, it has this clear, almost deliberate destructive goal. It's that paradox that makes them so incredibly fascinating. Probably the best way to wrap your head around it is to think of a virus as a biological ghost in the machine. It's just a set of instructions, a blueprint, tucked inside a delivery vehicle. So in this explainer, what we're going to do is build a virus from the inside out, piece by piece, to really understand how this non-living hijacker actually works. So our journey has to start at the absolute heart of the matter, with the most essential piece of the puzzle, the instruction manual that drives this whole entire operation. And here it is. This is the viral genome. It's the software, the code, containing every single instruction the virus needs to take over a cell and build thousands of new copies of itself. Now, there's a really important rule in the virus world, and it's this. A virus will have either DNA or RNA, but it never, ever has both. And that one simple fact basically defines its entire game plan. And these blueprints, they are definitely not one size fits all. Viruses have come up with this incredible variety of ways to store their code. You've got your double-stranded DNA viruses like herpes virus, and then you have single-stranded RNA viruses like SARS-CoV-2 and the flu. Each and every one of these genome types needs a totally different strategy to hijack a cell, which just goes to show you how adaptable these little machines really are. Okay, but a blueprint is totally useless if it gets damaged, right? So let's move on to the next layer and see how this thing is built, the protective armor that shields that precious genetic code. This armor is called the capsid. It's basically a rigid shell made of all these little interlocking protein subunits. Now, its number one job is protection, of course, but it's also absolutely critical for helping the virus latch onto and invade a host cell. So you can think of it as both a shield and kind of like the key to the front door. Now, viruses are absolute masters of efficiency, and over time, they've pretty much settled on two incredibly elegant designs for this armor. The first is the icosahedral shape. It's a 20-sided structure, kind of like a microscopic soccer ball, and it's super strong and stable. The other common design is helical, which is more like a spiral staircase that winds around the genome, keeping it safe inside. But then you get the exceptions, and these things are just wild. Take the T4 bacteriophage. This is a virus that infects bacteria, and it looks like something straight out of a sci-fi movie. It's got this complex structure that combines both designs, an icosahedral head to hold its DNA, and this long helical tail that acts just like a syringe to inject that DNA into its victim. It is a true biological machine. Okay, on to the final optional layer. And this is a really cool part, because this isn't something the virus builds for itself. It's something it steals. This is the ultimate tool for espionage, its invisibility cloak. It's called the viral envelope. So as a new virus is bursting out of a host cell, it literally wraps itself in a piece of the cell's own outer membrane on its way out. This is just a brilliant act of thievery, right? It creates this perfect disguise, which makes it way harder for your immune system to spot the invader. But this stolen cloak isn't just for hiding. Oh no, the virus sticks its own special proteins into it. Yep, the infamous spikes. These things, these glycoproteins, like the spike protein on SARS-CoV-2, they're the master keys that are designed to find and unlock the door to the next cell, allowing the invasion to just keep on going. Okay, so here's the crucial point. There's a trade-off. That stolen lipid envelope is actually pretty fragile. It's easily destroyed by stuff like detergents, heat, and just drying out. This is exactly why washing your hands with soap is so incredibly effective against enveloped viruses like the flu and coronaviruses. The soap literally rips their disguise apart, and they just fall to pieces. So we built our virus, it's got its blueprint, it's got its armor, and it might even have a disguise. Now, it's time for the heist, the full-scale invasion of a host cell. The whole plan is just ruthlessly efficient, and it unfolds in 6 basic steps. First, it attaches and gets inside. Then it uncoats, releasing its genetic blueprint. And that's when the real takeover begins. The virus hijacks the cell's own factories, forcing them to stop everything they're doing and start churning out viral parts instead. Finally, thousands of new viruses are assembled and released, all ready to go out and repeat the cycle. Now, once it's inside, a virus can choose one of two paths. The lytic cycle is the smash and grab approach. Just make copies as fast as possible and then burst the cell open to release them all. But some viruses play the long game. They use the lysogenic cycle. This is the sleeper agent approach, where the viral DNA silently slips into the host's own genome. It just lies dormant, getting copied every time the cell divides, waiting for just the right moment to strike. So we've seen how the virus is a master of minimalist design, right? But to really, truly appreciate its structure, let's look at something even stranger, something that operates on an even more bizarre and fundamental level. So just think about this for a second. What if you could have an infection without any genetic material whatsoever? No DNA, no RNA, just a single rogue agent that sets off a chain reaction of pure destruction. Well, say hello to the prion. This is not a virus. It's simply a protein that has folded into the wrong shape. That's it. But here's the terrifying part. This misfolded protein is infectious. When it bumps into a normal, correctly folded version of itself, it forces that normal protein to misfold too, setting off this devastating cascade that literally destroys brain tissue. And looking at this really brings into focus what makes a virus a virus. A virus is, at its heart, a genetic parasite. It has a blueprint, and it hijacks a cell to copy that blueprint. A prion has no blueprint. It's an infectious shape, a physical corruption that just spreads by touch. Understanding that difference really solidifies what a virus is and what it isn't. So in the end, the virus really stands alone. It's not some devious creature with a mind of its own. It's just a piece of elegant, brutal, and stunningly efficient biological machinery. It's a minimalist marvel, stripped down to nothing more than a blueprint and a delivery system. The ultimate survivor, forever existing on the very, very edge of what it means to be alive.